In this video, we're going to start out talking about acid and base chemistry and a concept called pH that's important in understanding how acids and bases are described. Let's just review our definition of acid and base. Arrhenius, the original definition of acid-base, an acid was a compound that ionized in water to give H plus ions. So this is what Arrhenius originally thought, that there were some molecules, like hydrochloric acid, that would decompose into ions, hydrogen ions and chloride ions. What we now know is what was really happening is these substances were reacting with water and producing the hydronium ion, that's that H3O plus ion, and chloride ion. But the model that Arrhenius formulated is still just as viable of a way of thinking about it, even though it's not actually what's happening at the molecular level. A base is a compound that dissolved in water to give hydroxide ions, OH minus ions. So that pretty much just meant soluble hydroxide salts, like sodium hydroxide. You put that in water, sodium salts are completely soluble, so you get sodium ions and hydroxide ions. A more expansive definition is the Bronsted-Lowry definition, and that's the one that we're going to use as our standard way of thinking about what an acid and a base is. In the Bronsted-Lowry definition, acids are proton donors and bases are proton acceptors. So in this reaction here, what we can see happening is this substance is donating a proton to that substance. So this is an acid, and then this is the base, because this donated a proton, that accepted the proton. And then afterwards, there's the species that has had the proton donated. It has one more H, and it's one more step positive. And then this is the species that's left over after the acid donates the proton. So when a base accepts a proton, it becomes an acid. When an acid donates a proton, it becomes a base. These are called conjugate pairs. So the base, NH3, has a conjugate acid, NH4 1+. The difference between these is one proton. You can see that there's one more H and one more step positive on the acid than there was on the base. The acid here, acetic acid, has a conjugate base. That conjugate base is one less hydrogen atom and one step more negative. Water itself auto-ionizes. It functions as an acid and a base. So water reaches a dynamic equilibrium with these two ions, H plus and OH minus, or hydronium ion and OH minus ion. Kw is the special name we give to the equilibrium constant, the Kc, for this particular equilibrium. It's called the ionization constant of water, or the ion product constant of water. What's actually happening here is that two waters are reacting with each other, and one water is donating a proton to the other water. But it's perfectly fine to think about that model when we're visualizing Kw. It just means that Kw could also be thought of as hydronium ion concentration times OH minus concentration. So at 25 degrees C, Kw is 1 times 10 to the minus 14th. That's the value of Kw. Now this changes with temperature. We know that equilibrium constants can change with temperature, but at 25 degrees C, which is pretty much room temperature, it's very common temperature, this is the value of Kw. And in a neutral solution, what it means by it being neutral is that the concentration of H plus and the concentration of OH minus are the same. So the question here is, what are the concentrations of OH minus and H plus in a neutral solution? Well, if they're the same, then Kw is 1 times 10 to the minus 14th. We could just say maybe x squared, because concentration of H plus and concentration of OH minus, they're the same number. Let's just call it x. And so if we take the square root of both sides of this, then we can find out what the value of x is, which would be the concentration of H plus, and it would also be the concentration of OH minus. And the square root of this is 1 times 10 to the negative 7th. So that's the concentration of both of these at equilibrium. Let's look at a solution that isn't neutral. In an acidic solution, the concentration of H plus ions is greater than the concentration of OH minus ions. What's the concentration of OH minus in a solution where the concentration of H plus is 1 times 10 to the minus 6th? Well, we know that Kw is 1.0 times 10 to the negative 14th, And that is going to be equal to the H plus concentration, which is 1 times 10 to the negative 6th, times the concentration of OH minus. So if we solve this equation for the concentration of OH minus, we find out that it is 1 times 10 to the negative 8th. In a basic solution, by contrast, the concentration of OH minus overpowers that of H plus. What's the concentration of H plus in a solution where OH minus concentration is 1 times 10 to the minus 4th? We'll do it the same way. Kw, which is 10 to the negative 14th, is equal to 10 to the negative 4th times the H plus concentration. Solve this for H plus concentration, and you find out that H plus concentration is 10 to the minus 10th. And it's 1.0 times 10 to the minus 10th. We're just preserving this number of significant figures there. The next important concept is based on something called the P function. The P function is an operation where we take the negative base 10 logarithm of anything. So pH is the negative base 10 logarithm of H plus concentration. Or, equivalently, we could say pH is the negative base 10 logarithm of the H3O plus concentration, because those are equivalents just in the two different models. pOH is the negative of the base 10 logarithm of OH minus concentration. So, thinking about the definition of pH, let's ask ourselves, what's the pH of a neutral solution at 25 degrees C? Earlier we saw that the concentration of H plus at equilibrium is 1.0 times 10 to the negative 7th molar. So pH is the negative base 10 logarithm of 1 times 10 to the negative 7th. When the mantissa is 1, this is really easy to do. You just look at the exponent and change the sign to a positive number. So this is 7. Now I'm going to write it as 7.00, and here's why. The significant figure rule is when you take the logarithm of a number, the number of significant figures in the number you're taking the log of, that's the number of decimal places you should have in the number after you've taken the log. So I have 2 significant figures in 1.0, so I'm going to write this to 2 decimal places. That's just a significant figure rule. Next question is, what's the pH of an acidic solution in which H plus is 10 to the minus 6th? So because the mantissa is 1, it's easy to do this. It's just that the pH is just going to be 6. Take that power, change it to a positive sign. And because I have 2 significant figures in my mantissa, I'm going to put 2 decimal places in my number for pH. What's the pOH of this solution? Well, to do this, we have to find out what the OH minus concentration is. We've done this problem before. OH minus concentration is 1.0 times 10 to the negative 8th molar. So that means the pOH is equal to 8.00. What's the pOH of a basic solution in which the OH minus concentration is 1 times 10 to the minus 4? This is pretty easy to do. pOH is going to be, look at the exponent, change the sign, 4, 2 decimal places because I have 2 sig figs in the number I'm taking the log of. What's the pH of this solution? Well, we saw that earlier when we figured this out, concentration of H plus is 1.0 times 10 to the negative 10th molar. So that means the pH is going to be 10.00. Well, sometimes we have the pH and we want to know what the concentration of H plus is. Here's an example. If the pH is 4.74, what is the concentration of H plus? If we take this equation here, pH equals negative base 10 logarithm of H plus concentration, and solve it for H plus concentration, first thing we can do is we can divide both sides by minus 1. So negative pH is equal to base 10 log of H plus concentration. And then to get rid of the logarithm, let's raise 10 to both sides. So on the left-hand side, it's 10 to the negative pH, and on the right-hand side, it's 10 to the log of H plus concentration, which is just H plus concentration. So the H plus concentration is 10 raised to the negative pH. So in this case, 10 raised to the negative 4.74 is how we would calculate that. And that comes out to 1.8 times 10 to the negative 5. And I rounded the mantissa off so that it has 2 digits in it because I have 2 decimal places. So the significant figure rule works just the opposite way. If you take 10 to a number, however many decimal places you have in the number you raised 10 to, that's how many significant figures you should have in the result. Let's think about the pHs of strong acids and then the pHs of strong bases. So first of all, for strong acids, the thing that makes an acid a strong acid is that it completely dissociates. Remember, we have 6 of these that do that. HCl, HBr, HI, HNO3, H2SO4, and HClO4. Those are the 6 strong acids. They completely ionize. So that means the concentration of H plus that you have is going to be equal to the concentration of HA, because every single mole of this will turn into a mole of H plus. So the pH of a 0.1 molar solution of HCl would be the pH of a solution where the H plus concentration is 0.100 molar. So that means pH would be the negative base 10 logarithm of 0.100. And this turns out to be 1. There are 3 significant figures in the number that I took the log of, so I should have 3 decimal places in my pH. pH of strong bases. Strong bases are all going to be ionic compounds that have hydroxide ion as their anion. So that might be a +1 cation, a group 1. So you get 1 hydroxide for every mole of MOH, where M stands for some group 1 metal. There might also be 2+ group 2 metals. Well, in that case, it's going to be a formula where there are 2 hydroxide ions released for every mole of the metal hydroxide. And so you would end up with 2 times the concentration of the metal hydroxide for our OH minus concentration. And if it was 3+, like aluminum hydroxide, for example, then you'd have 3+. So we could say that whatever N is in this formula, that's going to be how many times you should multiply the concentration of the metal hydroxide by to get the OH minus concentration. So what's the pH of a 0.01 molar solution of calcium hydroxide? Because this is releasing 2 moles of hydroxide for every mole of calcium hydroxide, that means that our concentration of OH minus in this solution is going to be 2 times 0.010 molar, which is 0.020 molar. Now we want the pH, so what we want to do is we want to take Kw and divide by that OH minus concentration to give us the H plus concentration. So that's 1 times 10 to the negative 14th divided by 0.020, which comes out to 5.0 times 10 to the negative 13th. So that means our pH is the negative base 10 logarithm of that, and that comes out to 12.30. Let's take another look at relating pH and pOH that can sometimes give us a very valuable shortcut. Thinking about what Kw is, it's the concentration of H plus times the concentration of OH minus. If we took the P of both sides, so negative log Kw equals negative log H plus times OH minus, we would be doing this. Negative base 10 logarithm of 1.0 times 10 to the negative 14th equals negative base 10 logarithm of H plus concentration plus negative base 10 logarithm of OH minus concentration. Because when you take the log of a product, that's like taking the sum of the logs of the things that are multiplied together to make that product. Well, log of 1 times 10 to the minus 14 is just going to be 14, negative 14, but we change the sign because it's a negative log. And the negative log of H plus concentration is pH, and the negative log of OH minus concentration is pOH. So what that means is that 14 is the sum of any pH and pOH for the same system. So if we wanted to know what's the pOH of a solution where the pH is 4.74, we can use this equation and say 14 minus the pH, which is 4.74, is going to be equal to the pOH, and when we do that, we come up with 9.26. One last topic for today. Let's talk about the solubility of ionic compounds and how pH can affect it. So let's think about some different species that are dissolving. These are partially soluble salts. And which ones would have different solubilities in different pH conditions. Here's one option: calcium hydroxide, calcium fluoride, lead iodide, and silver phosphate. The only one that's going to be affected by pH is the one that has hydroxide ion in it. Why would it be? Because If we had a high pH, then that means we have a lot of hydroxide ion present in the solution. And that makes hydroxide ion a common ion, and we know that that reduces solubility. So an excess of hydroxide ion is going to shift this equilibrium between calcium ions in aqueous solution and hydroxide ions in aqueous solution to the left. There's too much OH minus that's going to shift it this way, and it's going to reduce how much calcium hydroxide can dissolve. If you were in a low pH environment, then what's going to happen is you're going to have a lot of extra H+. What's H+ going to do when it gets together with OH minus? It's going to produce H2O. And this is almost a one-way reaction because the K for the reverse of this is very small, 10 to the minus 14th. So that makes this a very large K. So we're going to have mostly water and very little H+ and OH minus after this equilibrium is established. Well, that means that you're reducing some OH minus, taking it out of the system because you've reacted with H+ that was in our low pH environment. That would cause a shift to the right, so in low pH, calcium hydroxide would dissolve better. Let's look at a quantitative example. Iron 3 hydroxide, which has a KSP of pretty small, 4 times 10 to the minus 38th. Let's look at what would be its solubility in two different pH environments. Let's say that the pH was 5. If the pH is 5, then that means the pOH is equal to 9. So that means the OH minus concentration is equal to 1 times 10 to the negative 9. Now let's set up a rice chart. We have FeOH3 in equilibrium with Fe3 plus and 3 OH minuses. Initial concentration, don't care about the solid, this will be 0. But in our situation, we have 1 times 10 to the minus 9th as our starting concentration of OH minus because the pH is 5. What's our change line? Minus x plus 3x. At equilibrium, iron concentration is x, and the hydroxide concentration is 1.0 times 10 to the negative 9th plus 3x. So KSP, 4 times 10 to the negative 38th, is equal to concentration of iron, which is x, times concentration of OH minus, which is 1 times 10 to the negative 9 plus 3x cubed. But 4 times 10 to the minus 38 is really, really small, so 3x is going to be very small compared with even 1 times 10 to the minus 9. So we could rewrite this as 4 times 10 to the negative 38th. It's going to be pretty much equal to x times 1 times 10 to the minus 9 cubed. And then you can solve this for x pretty easily. And it comes out to 4 times 10 to the negative 11th. So that means the amount in moles per liter of iron hydroxide, iron 3 hydroxide that you could dissolve in pH 5 would be 4 times 10 to the minus 11th. Okay, let's keep that in mind and look at a different situation. What if the pH was 11? Well, if the pH is 11, then that means that the pOH is going to be equal to 3. So that means the concentration of OH minus on your initial line in the rice chart would be 1 times 10 to the negative 3rd. So then we don't have to do the rice chart because we can probably remember what it came down to. It came down to 4 times 10 to the negative 38th, that's KSP, is equal to x times the starting concentration of hydroxide, 1 times 10 to the negative 3rd, cubed. With that simplification, that 3x would be small compared with the starting concentration. When we solve this, x comes out to 4 times 10 to the negative 29th. And if we compare those values, we can see that at the high pH, in fact, the solubility of iron 3 hydroxide is much lower than when the pH was lower. And it's all due to the common ion effect.